likely what's going to happen your next exam on the Unit 2 gastrointestinal stuff will be in a couple of weeks from now, whatever date it is. I don't remember 4 weeks ago, right? And the exam number 3, which is a smaller one, will follow soon because it's on metabolism and it's kind of simple. Okay. Here. So what I would like to do today is to review the main processes that happen in the stomach, okay? And then regulation of this digestive activities in the stomach, regulation of digestive activities in the duodenum, like that. So a few things to say about the stomach anatomically tissue. We've got the esophagus, right? Then we've got like this bag, which the stomach is, and then we've got a duodenum, right? A few things. First of all, stomach and esophagus are separated by a sphincter. This is the gastroesophageal sphincter, and this part of the stomach right here is called cardia. This part right about here called fundus. This part of the body, and this part is pylorus. Pylorus can be further divided into pyloric antrum and pyloric canal. You can see it all on the anatomy on the slides. I'm not going to pay too much attention to it. What I wanted to highlight more or less, is that these parts of the stomach, they all have slightly different activities in terms of the digestion. Think of it this way. So cardia, food just gets in the stomach from the esophagus. In that part, the cardia, there's not really much of a digestion. Does that make sense? Because it's just got there, okay? So not much of the digestion. Okay. Then we've got pylorus. At this point, look, the food, we're not calling it a food, we're calling it chem, C-H-Y-M-E, okay? Chem is about to get into the duodenum through the pyloric sphincter. Now, at that point, there's not much digestion either, because, you know, it's kind of too late, right? Because the food is about to get into the duodenum. It's not, digestion is not like superficial here. So not much. In pylorus, not much of the digestion. So the main digestive activities, they occur in the fundus and the body. Does that make sense? Okay. A couple more sort of anatomical details about stomach. It has a typical 4-layer wall. The big difference of the stomach compared to other parts of the digestive tract is that it has 3 layers of smooth muscle tissue. It has circular smooth muscle, longitudinal smooth muscle, and oblique smooth muscle. And that gives the stomach the capacity to really actively move the human side. Good so far? Good. So there's a circular layer, longitudinal layer, and oblique layer. Oblique is diagonal layer that, you know, it all really keeps up a notch a process of mechanical digestion. So far, we're good? Okay. So what are the cells? The epithelium, and what are the cells? So epithelium, simple columnar. Now, what are these cells? Cells are regular, just, sort of, you can call them absorptive cells. There's not much of an absorption that goes on in the stomach, just garden variety columnar cells. Okay, we've got goblet cells. Okay, so goblet cells produce mucus, and not just it's a alkaline, thick mucus. You may wonder, of course, why? Well, you know that stomach is acidic; it has an acidic environment inside of it. So this thick alkaline mucus protects the epithelium from the aggressive environment in the stomach. That makes sense. And then we've got renal cells and chief cells. We have, I'm going to put here, ECL cells, which are endocrine cells. So renal cells produce hydrochloric acid. Okay, chief cells sort of produce carcinogen. And gastric metals. Renal cells release hydrochloric acid, and they also produce something called intrinsic fat. I'm going to talk about that. Does that make sense? Now, if you think about, the functions of different cells, so obviously, goblet cells produce mucus. They're going to be distributed fairly evenly across the stomach. Now, renal and chief cells, cells that actually produce components of gastric digestive juices, where you can expect those cells to be present. Of course, in the fundus and in the body, where most digestive activities occur. Does that make sense to you? Got it? Now, what about these regulatory cells, endocrine cells? So these endocrine cells will be concentrated mostly here in the pylorus, okay, because that will be a key regulatory part of the stomach, and we'll get to this. I forgot one more cell type is G cells that produce gastrin, and we never mentioned what ECL cells produce. They produce these things. Now we have more or less complete picture. Okay? So far, we're good. That's kind of generally cells that participate in the digestion. So, what we're going to start with in terms of like physiology of the stomach, we're going to talk about the regulation of digestive activities by different hormones. And then we're going to talk about how carcinogen, gastric lipase, hydrochloric acid, what they do. Okay? So let's start with we'll try to paint a big picture of how digestive activities in the stomach are regulated. And of course, we're going to start with a fluid in the stomach. Does that make sense? Now, as we discussed before, presence of food in the stomach. What kinds of receptors can it stimulate? Chemical and mechanical. Yes, chemical and mechanical receptors. Makes sense, right? Now, what are the effects? So it's going to act on two structures. One of them is going to be medulla oblongata, and the signal to the medulla oblongata will go through the vagus nerve, so cranial nerve 10. Okay, and then medulla will produce a response, which will go also through the cranial nerve 10 to the vagus nerve. This is why this digestive reflex, look, this digestive reflex is called vagal reflex. Are you with me? Vagal. Yeah, sure. So vagal reflex, meaning that, you know, vagus nerve, medulla vagus nerve thumbing. You get so far? And also, of course, those receptors will send the signal to local plexus. And the effects of signals from medulla oblongata and from local plexuses will be somewhat similar. It will lead to increased mechanical digestion, first of all. Okay? Now, mechanical digestion in case of stomach is called churning. If you think about other parts, like if you think about intestine, think of intestine as tube, right? As a long hose, right? So once food, well, not a food, it's chem. Once the chem gets in the intestine, the only way for the chem in the intestine is to move forward. Does that make sense? In the stomach, if you think of the stomach as a giant bag, well, not a giant bag actually, but a small bag, food in the stomach will be going in circles. Does that make sense? Like in a, because it has to be mixed well with the gastric juices, and only small portions of that chem will move on from the stomach to the intestine, once at a time. Are we clear about that? We're good. So the main mechanical digestive activity in the stomach is churn, to move the food around, to make sure that it's properly broken in pieces, you know, and it's well mixed with the gastric juice. Now, in second effect of this stimulation, local plexus and medulla oblongata, increased gastroesophageal. Okay? Which has actually, quite interestingly, a lot of effects. So, which cells produce gas? What's a G cell? Now, elevated levels of gas will stimulate PCL cells, and they will produce histamine. Okay? Are you following? And then histamine will stimulate elevated levels of hydrochloric acid, but the renal cells have elevated levels of enzymes. Are you following? Good? Got it? So again, we've got stimulus. This processes the local level or level of the central nervous system. It stimulates G cells, which is gastrin. The gastrin stimulates the CL cells, which is histamine. Histamine stimulates renal cells, which is hydrochloric acid, and Q cells, which is enzymes. So far, we good? Okay. And that leads to the digestion. We'll talk about hydrochloric acid and synergy later. Super important. That makes sense. Well, it turns out, on the gastrin, there's a variety of other effects on other parts of the digestive system. So, right now, we have food in the stomach, right? And ultimately, if we have a food in the stomach, eventually, this food has to be moved down the road into the small intestine. That makes sense. But there is a pretty good chance that you have some heme, some digestion going on at that particular moment in the small intestine, right? And you have some stuff in the large intestine that is about to be formed as feces. Am I clear? Because the process of digestion is not like a discrete process. You do not have your digestive system completely empty unless you're like fasting for several days. You do not have it completely empty. So there's something going on in the intestine, a little bit of stuff going on in the colon. Does that make sense? So since you're going to send some of that heme down into the small intestine, you need to open the sphincter between the small intestine and the large, between the stomach and the small intestine. Does that make sense? Is that clear? We need to open the door. So gastrin actually stimulates the lower sphincter relaxation. Makes sense, right? Now, how do we get the stuff in the small intestine to move down the line? We call it peristalsis. Are you following me? So in order to move the content of small intestine down the road, gastrin increases intestinal peristalsis. Okay? So far, you follow me? Intestinal peristalsis goes up. So all the heme that's in the small intestine and in the large intestine, they start to move to the very end, towards the ends. Good? Good? Understood? Okay. Now there's another sphincter that separates small and large intestine, so-called ileocecal valve. So gastrin will relax ileocecal valve. Okay, we're good so far? And finally, think of it. All the stuff that's in your colon, you know the colon, like very, very distant part of the intestine. All the stuff that's in your colon, basically, you need to get them out. Does that make sense? So gastrin will also stimulate I'm going to talk very bad. Gastrin is going to equal mass movement. Mass movements are really powerful contractions of smooth muscles in your colon that expel feces, essentially. You know, they push colonic content towards, they push colonic content towards the anus so you can take. Does that make sense? So basically, what I'm trying to tell you is that when you eat, and food eventually gets all the way down into your stomach, and that stretch, mechanical stretch and chemical changes in your stomach, when they stimulate gastrin, the effects, they reverberate throughout your digestive system. You see what I'm saying? Your stomach starts to churn, your small intestine starts peristalsis, the sphincters become relaxed so the food can move on, and your large intestine starts to propel the feces towards the mouth. Okay. This actually explains why often there's an urge for the bowel movement right after you eat. Makes sense, right? The good so far. Now, I have a pretty simple question right here. When food gets in the stomach, what kind of chemical change occurs there? What happens? Let me be more specific. What happens to the pH in the stomach when food gets into the stomach? Excellent. It increases. Very, very good. Because food essentially lowers the concentration of acid, therefore increasing pH. Does that make sense? So we can effect that increased pH. Gastroesophageal. Does that make sense? Are you following? Like that's what it is. Does that make sense? Now, look at this processes. So pyloric sphincter relaxation, increased intestinal peristalsis. So the food from the stomach can get into the small intestine. This whole thing is called gastric empty. Okay, we get F here, but more like saying gastric empty. Okay. We're gonna go over this. My plan is we're gonna draw a massive scheme here. And then all interconnected scheme, we will review all the aspects of gastric digestion. So far, you following me? So where we're at now, we figured that elevated pH will stimulate gastrin, basically directly, right? Now, what else can serve as the stimulus, except for the food in the stomach? If you think about the stimulus for digestive activities, often you do not need to actually put any food down the drain. Does that make sense? You understand what I'm saying? All you need to do, actually, is to look at it, or smell it, or taste it. Make sense? So we can say that we're going to combine the reflex here. I'm going to say smell, taste, cycle. You good? Now, are you going to perceive it? You're going to perceive it by the brain, and then it will send the signal to the brain. Does that make sense? I'm going to take, please, if you're not really following, please let me know. So I want to highlight a couple of things. So this, anatomic, which body part sees food, smells food, and tastes? Which body part? Huh? Excellent. Your head, yes. So this is called a cephalic stage or cephalic phase. Cephalic phase of the regulation for digestive activities, gastric digestive activities. Does that make sense? Now, this part. That's going to be gastric phase. Does that make sense? And now we have a third phase, which is intestine. And we're going to figure out how your intestines affect this central step here in the cell. Right? Okay. So what happens? As a result of gastric emptying, remember the term heme? Remember that term? Heme ends up in the duodenum. That's the part right after the step. Now, presence of heme in the duodenum has two very interesting effects. There's a short term and a long term effect. I'm going to do this arrows back, and it's going to be short. So in the short term, heme in the duodenum stimulates gastric emptying by a stimulation of gastrin. Let me explain why. Imagine that a leaf is a stomach, okay, and I am the duodenum. Therefore, she starts to send me a little bit of a kick. And my initial response will be, give me more, keep going. If that makes sense. So this is a short-term stimulation of gastric emptying and gastric production. But as a digestive organ, the duodenum, can handle only a very small amount of kick. So when this small amount gets into me, I switch to sort of long-term regulation that tell my stomach, stop, we're good, hang on, close everything, no more gastric emptying. Okay, so that's long-term inhibition of gastric emptying and long-term inhibition of gastric production. And sorry, that will be intestinal. It's not enteric. Huh? Are you with me? Now, let's review this. Pretty complicated picture. I know. So I can explain why it this kind of looks so complicated, because usually we talk about each part individually, but I try to put all picture together with you step by step. So let's start with the head. When you see, smell, taste the food, that signal goes through your brain. Brain, if you find the food appealing, it's not something terrible, if you find it appealing, it goes to medulla oblongata, and from medulla to the vagus nerve, it stimulates mechanical digestion in your stomach. Does that make sense? And it stimulates secretion of gastrin by G cells. The good? Gastrin stimulates histamine stimulates hydrochloric acid and enzyme production. You've got your chemical digestion in the stomach. Are we clear? On top of that, gastrin stimulates gastric emptying, so heme gets delivered into the intestine. It stimulates opening of pyloric sphincter, increased intestinal peristalsis, relaxation of the bowels down the road, and mass movements in the colon. So basically, it initiates, it sets the intestine in motion. Does that make sense? The whole intestine is set in motion. So heme from the stomach can get in the duodenum, and there's going to be good. Now, meanwhile, food gets in the stomach, increases pH, leads to the stretch of the stomach, and through the local plexuses and through the medulla oblongata, all the same stuff happens. We're good? Then, so that's going to be your gastric phase. So basically, I can tell you in the gastric phase, food in the stomach increases pH, stimulates production of gas, blah, blah, blah. Okay? Finally, intestinal phase. In the short term, immunoduodenum stimulates gastric activity, but in the long term, inhibits it. In the short term, immunoduodenum will stimulate secretions in the stomach. Does that make sense? But in the long term, it will inhibit all the secretory processes. Are we clear? Questions? Yes. So, yeah. So, say this is how much Kim I as intestine can handle. So you as a stoma start to pour Kim into this like that hole, okay? Because you're pouring and I tell you keep going, keep going, keep going, then it reaches the top and the sensors in the intestine say, stop. Stop. Now you need to chill because we need to deal with that amount. Your intestine handles actually very little. I'll give you an idea. A portion of Kim that goes in sort of a one attempt, you know, like once, in your intestines, like milliliters. So imagine you had a, for that matter, like I had a yogurt. What's it? About 100 mils. You know, like if I had only yogurt plus all the gastric juices, so out of all that volume that I have in my stomach, every time only 3 milliliters will be pushed into the intestine. Because we need very small amount to be spread over surface to be efficiently absorbed. Does that make sense? That's really important. You got it, please? So in the long term, like those 3 meals were delivered and intestine tells to stomach, hey, shut it. I mean, you keep going, like, stomach keeps digesting, just shuts down the communication with the intestine. Make sense? Like sphincter closes, gastrin levels go down a little bit, you know, all the peristalsis in the intestine kind of ceases, all that stuff ceases. Then, you know, another portion of Kim is ready, moves into the duodenum, you have the same effect. The thing is, probably what I should say here, it's not a continuous, it's not a flow. It goes in waves. One wave, one portion, then another portion, then another portion. Does that make sense? Did I answer your question? Good. Next question is, if some stuff can stimulate digestive activity, what do you feel? How do we call that feeling when you want to? Huh? Hunger. Okay, when you're hungry, you have appetite, right? When you're hungry and you see food, that's going to stimulate your digestive activity, right? But imagine that you're not hungry. if you don't have any appetite, the sight or smell or taste of food, not going to trigger this. Does that make sense? You understand? So I'm going to put in blue color stuff that does not stimulate or even inhibit. On the cephalic level, depression and lack of appetite. Now, one of the most important things that will inhibit gastrin secretion, if elevated pH stimulates production of gastrin. So what will inhibit production of gastrin? Yep. Low pH will inhibit production of gastrin. Does that make sense? Well, and on the intestinal level, we kind of figure long-term nutrition. You good? Clear? Okay. Excellent. Now, good. Realistically, nothing if you're not trying to drink acid. But it's basically more of a negative feedback type of response, because think of it this way. When you eat, and that's a good question. When you eat, the pH goes up, as Katie mentioned, right? The pH goes up, gastrin secretion goes up. Gastrin secretion goes up, production of hydrochloric acid goes up. Production of hydrochloric acid goes up, the pH goes down. That controls gastrin secretion, so it doesn't go into overdrive. Make sense? I mean, obviously, if you decide to drink acid, then you. But I think in this case, your gastrin production will reduce the problems. Good? So I'm gonna get rid of it. Yeah, sure. It's also just I'm gonna be posting these recordings. So all those on YouTube that are special separate channel. Not channel, no, yes. Not no. Maybe a shitload of Fanta would work, because Fanta has a pH of about 2.5. Your stomach is about 3, so we'll drop it a bit. Orange juice is about 4, so it's not as acidic as as the, hydrochloric acid. I drank hydrochloric acid once accidentally, not a huge amount, and I mean it was fine, just because the concentration of the stuff that I drank accidentally, the volume was pretty low. Yes.
So we talk about gastric.
Yeah. Yes.
So if those like smelling food,
It will stimulate, yes. It will stimulate all the digestive processes in your digestive system. Absolutely. Smelling, seeing, yeah. And this is one of the reasons why, it is recommended, like if you want to chew gum, make sure that you have something in the stomach. Otherwise, you just stimulate the production of acid just in the stomach. And that may lead to, let's like get it out of the way, esophageal, gastroesophageal reflux, when acid goes up in your esophagus. Mostly the reasons are either, exercise, you basically just bump the stuff up. Sphincter is not tight to seal, so it can be set up. Some folks' sphincter is not closing tight enough, so they have a problem with reflux. Or acidity in the stomach too high. You can overeat, for example, it's overstretched. the main risk associated with regular gastroesophageal reflux, and I want to highlight regular, is that when acid spills over into the esophagus, it damages the epithelium, which leads to local inflammation and scarring. And chronic inflammation is a risk factor for esophageal cancer. Okay, so that's it. Yeah, if it's regular, then yeah, it should be addressed. Otherwise, it's not. Big issue. Okay. So let's address some of the concepts related to the processes, these chemical processes that happen in the stomach in terms of the digestion. So first, we're going to figure out how hydrochloric acid is produced in the stomach. So imagine that this is your typical. Oh, by the way, speaking of which, remember we had this chain of events: gastrin, histamine, histamine-actin cells. Well, what effect do you think drugs like Benadryl, if you overdose on Benadryl, what effect this overdose will have on your digestive system? One of the side effects of kind of Benadryl and other antihistamine abuse are constipation. It just doesn't digest. Make sense? But it should be abused. It's not going to be a side effect of just taking Benadryl for allergy. Okay, so parietal cells. Let's say you've got a blood vessel here. That's your parietal cell. That's the lumen of the stomach. Are you full? The lumen of the stomach means that's empty space inside of the stomach. Here's what happens. You need to produce hydrochloric acid. The most abundant acidic compound that you have in your body is carbon dioxide. So you have carbon dioxide from the blood diffusing into the parietal cell. In the parietal cell, carbon dioxide will interact with water, forming carbonic acid, which then will dissociate into bicarbonates and hydrogen ion. Now, hydrogen ion is essentially an acid. Bicarbonate is essentially a base. Does that make sense? So, what do you need? You need acid. Hydrogen ions go into the loop, and whether you get bicarbonate, dump it in the pool. If that makes sense. Absolutely. So you've got CO2. You have abundance of CO2 in the water. That's wasteful, right? CO2 normally diffuses into the parietal cell. And in the parietal cell, CO2 will interact with water, forming carbonic acid. You see carbonic acid right here? If you're curious, I'm not going to ask for some example. If you're curious, this step is critical. There's an enzyme that actually facilitates that. Carbonic acid will quickly dissociate into bicarbonate and hydrogen ion. You good so far? You don't need bicarbonate at this point because that's in the blood. Now, hydrogen ion will get into the lumen of the intestine. And I want to put in the intestine, stomach, the lumen of the stomach. And I want to ask you, when it's going to get into the lumen of the stomach, what kind of transport it's going to be for hydrogen? Because remember, hydrogen is hydrophilic. It cannot get through the membrane directly. So the basic question is, what kind of transport it's going to do for hydrogen? Is it going to be facilitated diffusion, or is it going to be active transport? It's 50-50. Take a job. First of all, nobody's going to make fun if you got it wrong. I'll just tell you, no, that's right. No. If you got it right, that's immediate notification. So, facilitated diffusion. Remember, though, if you give a right answer, I will ask you to explain what it is. So, facilitated diffusion or active transport. What takes you so long? Huh? Good. Why? Well, remember what active transport is. The movement against the concentration gradient, right? Does that make sense? Are you following? Now, you're pumping acid into the stone. There's plenty of acid here already. Does that make sense? You're essentially moving hydrogens against their concentration gradient. You see what I'm saying? Makes sense, right? So this is why it's called active transport, and the protein that does this active transport is called a proton pump. You clear about that? This one. Good? Okay, okay, I mentioned intrinsic factor. Very briefly, intrinsic factor is the protein required for the absorption of vitamin B12 that's in the milk, such as I mentioned. Now, the next question is, well, the enzyme called gastric lipase doesn't need any clarification. Breaks down fast. Okay, now, what about pepsinogen? So pepsinogen is quite interesting. So pepsinogen is a precursor molecule. It is converted into active form, pepsin, by hydrochloric acid itself. And pepsin breaks down proteins, right? So we've got that there are two biological macromolecules, two nutrients that are digested in the stomach. So proteins digested by pepsin. And fats digested by gastric acid. So far, we're good? Got it? So kind of a little bit going back to what we were talking about. Remember I told you that cardia, pylorus, and fundus and body, they have slightly different functions. Cardia and pylorus, not much digestion, fundus and body, most of the digestion, right? Basically pylorus, that place where food goes before it gets into the intestine, that's where G cells and ECL cells, that's where these endocrine cells are located. Because when heme is about to enter small intestine, the G cells will stimulate gastric emptying, will release gastrin, will release histamine, and will stimulate gastric emptying. Does that make sense? So when I showed you this picture, well, when I drew this schematic of a stomach with, cardia, fundus, and body, and you have to understand, there's not like a line on the stomach that separates them. It's not a delineation in a sense that, you can say, okay, arm ends here and the trunk starts here, right? The delineation is by the cells that are mostly present in one or another region. You see what I'm saying? Like if you see a lot of G cells and ECL cells, oh yeah, that's pylorus. If you see mostly parietal and chief cells, so parietal and chief cells, oh yeah, that's fundus in the body, the digestive parts of the stomach. Does that make sense? Okay. Couple more. So one is one hormone that we didn't mention is a serotonin. It's in the nodes, also stimulated by the food in the stomach, and it increases digestive activity, increases churning in the stomach. Good so far? That's that. Peptic ulcer, you know, that condition probably, in some cases can be caused by overproduction of acid. Rare. And tumors can lead to that. Most, probably 99.9% of all peptic ulcers is the result of infection with bacteria, Helicobacter pylori. If you watch, you should watch today. I talk about a bit of a discovery of that condition, that causative agent and how it was linked to the disease. The point is, when we now have a patient with peptic ulcer, we treat this patient not only with proton pump inhibitor, but also with antibiotics and antibiotics. Does that make sense? Does that make sense to you? Specifically, only antibiotics and proton pump inhibitor, or not antibiotics per se, or not proton pump inhibitor per se. We need both. Does that make sense? Why you need both? Proton pump to reduce acidity, because if you have really acidic, you have that acidic environment keeps causing inflammation and damage in the ulcer, so you need to reduce that. And antibiotics to get rid of bacteria. If you don't get rid of bacteria, you're not gonna. You can cure it. It's curable. It's not true. It's curable. You get rid of the bacteria, it kills. The main problem associated with ulcer, obviously, as always with inflammatory conditions, cancer. It often leads to the development of gastric lymphomas and cell lymphomas. I think it's also going to cause it. Okay, we're good? Okay. So what I want to do now, I want to chat a bit about duodenum, discuss the hormonal regulation, and then after the break, talk about pancreas and liver and some absorption stuff. Okay? So, duodenum anatomy is unusual, right? Because there are two main concepts that I will review. Pretty short, about 10 inches. Most important digestive organ in the human body. In terms of digestion, in terms of absorption, absolutely critical, okay? And a few things. First, remember I told you that there are only 3 milliliters of heme that gets in the duodenum? Also, duodenum has enormous surface area, very well suited for efficient absorption. And that surface area is achieved by circular folds. I am not a good artist. I'm not going to draw this stuff. It's all in the notes. Circular folds serve two purposes. First, since they are folds, they increase surface area, right? And since they go like a thread on the screw, does that make sense? They move heme in a circular fashion. So it doesn't go straight through the duodenum, it stays there longer. See what I'm saying? Like if you go on the slide in a water park, it's not the same as you just drop down into the water from the same height. It will take you longer. Okay? Second, we have villi. So these are villi, little projections on the surface of the small intestine, the entire small intestine. Duodenum, jejunum, and ileum, 3 parts. They are rather small, about 1 millimeter long, so you can't see them with the naked eye, barely. And they give the intestine that velvety appearance. Okay. And finally, you can see that the surface of villi is covered with epithelium. It's a columnar epithelium. All right. So which cells are you going to find there? They're going to be absorptive cells. I don't think that we need to comment on what they do. Goblet cells for mucus production. Okay. Banner cells. These are cells, basically cells of the immune system, kind of, and enteroendocrine cells. Enteroendocrine cells, obviously, are responsible for enteroendocrine cells are responsible for production of enzymes. And the enzymes, so hormones. That makes sense. Got it? Now, one thing that I really want to make clear. So far, we talked about circular folds, we talked about villi, but there are also micro villi. This is a columnar cell, and those are the folds of the membrane on its surface. Can you see the folds? So that's called brush border, and each of these folds is called a villus. It's like tiny little hairy projections on the surface of the cell, which increase surface area of the small intestine even more. Am I clear? Now, brush border contains critical enzymes. You can think of it like their position here and here and there and here. Okay? Those are brush border enzymes. The function of these brush border enzymes is to break down bits of nutrients. Now, let me give you, I worked out a pretty neat analogy of how digestion of nutrients works. So think of it this way. When you eat, when you read the nutritional information on the package, what they say? They say proteins, fats, carbohydrates, right? Proteins are really large molecules with a lot of amino acids formed in a chain. Are you with me? Are you with me? Are you following me? So imagine the chain that is 100 amino acids. The role of your digestive system is to break it into 100 individual amino acids. Does that make sense to you? Got it? Now, my analogy, and I'm going to be using it, basically the same as you buy meat in the grocery store. Go to the grocery store, you buy meat there, and it's packaged in neatly, steak or loin or something, 2-3 pounds maybe if it's not possible, right? But if, let's say, if you buy pork, then it ultimately comes from a pig. So this packaged pork, if you compare it to digestive system, that's individual amino acids, individual monosaccharides, individual triglyceride molecule. Does that make sense? The pig is your massive protein molecule or a starch molecule. Am I clear? So what happens in your digestive system when this pig, and proteins are the most convenient things, when this pig gets all the way down to the stomach, pepsin that we just discussed, breaks it into chunks. So like a leg, right? Or 1/3 of a pig. Makes sense? Like you're not buying 1/3 of a pig. You need this stuff to be processed even further. Does that make sense? So the function of brush border enzymes is to finish the processing. They take those chunks and break them down to individual molecules, individual monomers, individual amino acids, individual monosaccharides. Does that make sense? So what would be the examples? For instance, the breakdown of carbohydrates. You have this list there in the notes. It gives you enzymes like sucrase or lactase. So what does sucrase break? It breaks sucrose, sugar. Does that make sense? What does lactase break? Breaks lactose, milk sugar. Maltase breaks maltose. Dextrinase breaks dextrin. Now, why base? Like, how many? What is sucrose? What is sugar? Sugar is a disaccharide. There's a molecule of glucose and molecule of fructose, and they link together. So what this enzyme does, splits them. Make sense? But that molecule, that disaccharide, may come from a huge polymer that you ate as a part of, I don't know, an apple or something. Does that make sense to you? Got it? Good. Same goes for, I'm not doing a full list. For instance, the enzyme called dipeptidase. Dipeptidase. Okay? Dipeptidase, two peptides, two amino acids together. Dipeptidase splits them into two individual amino acids. Does that make sense? Nucleosidases and phosphatases. So this is your garden variety nucleotide, okay? Phosphate. What does phosphatase do? Breaks down the bond here. What does nucleosidase do? Breaks down the bond here. So now I have nucleic acids broken down to nitrogenous bases, ribose or deoxyribose sugars, and phosphate. Does that make sense? What you need to know, and I will ask you can have a question. Which of the following enzymes does blah, 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 blah? Or the function of dipeptidase is to break down dipeptides into individual amino acids. Am I clear? Yes, you're going to get those questions, I promise. We need to know the function. I'm not going to ask you to write a list, like write me all brush-border enzymes, but you should know the functions of all brush-border enzymes. Am I clear? Good? Okay. So that brush-border here we go. The last bit before we go on the break. The regulation of digestive activities in the intestine by two specific enzymes. I keep saying enzymes, hormones, which are cholecystokinin and secretin. So, a trivial question that I asked many times already: what is the stimulus for digestive activities in any part of alimentary? Four-letter word that starts with F. Food. In this case, they have vomited. You know that even stuff that's in the stomach doesn't look like food anymore, right? It's pretty well digested. But the stuff that enters intestine is even less food-like. It's fairly homogeneous mix of gastric juices, which have what pH, by the way? Acidic. My principle, I practically do not ask to memorize any numbers. There are going to be some you will need to remember in the metabolism part. Other than that, screw it, screw it. Like, I don't care if it's 3, 2.5, or 3.5. Doesn't matter. Very acidic, right? Very acidic kill. That contains kind of semi-digested nutrients, including fat. You with me so far? So this is what we have. We have T. In the intestine. And it has two distinct features. Low pH and lipids. So this chemical stimuli induce a hormonal response from enteroendocrine cells. Look at this. Low pH leads to the production of secretin. Right? And fat leads to the production of cholecystokinin or CCK. Don't mind, I'm not going to write the whole name. It's all in the notes. Stuff that can be easily looked up. Go for it. Cholecystokinin. Let's figure out the role for a second. So, pH in the intestine is slightly basic. Here, you have acidic pH. What do you need to do with acid to make sure that pH of the intestine does not change? Huh? Get rid of it, neutralize it, right? And what do you neutralize acid with? Huh? Base. Very good. And what base is available to you in the body? Bicarbonate. So secretin will act on pancreas. And the pancreas will produce bicarbonate. Okay? And this bicarbonate will essentially start neutralizing the acid. Any sense? Are we clear? Another organ that secretin will act on, the liver. Secretin will stimulate just a little bit of a bile production. Why? Because bile also contains bicarbonate. Am I clear? Make sense? Now, what about CCK? Well, turns out that cholecystokinin is stimulated by lipids. And in order to properly digest lipids, a little bit, not really digression, but kind of a bit of an example. So imagine you have oil, canola oil, and you want to mix it with water. Is it going to mix well? No, it's not, because oil is hydrophobic, and it's going to form this giant blobs in the water, right? So, but if you will add soap, suddenly oil will become all soluble in the water, because you have this surface active compound, so that will break this giant blobs of oil in pieces, and we'll talk about that mechanism forming myceles, making it really, really well dispersed in water. Make sense? Environment in your intestine is water. It's hydrophilic. So in order to successfully digest fat, you need to solubilize it. Does that make sense? You need to break these giant chunks into tiny little pieces. How do you do that? CCK, and we'll get to the name, stimulates gallbladder to release bile. Now, you may notice, I have noticed that I didn't say to produce bile. Gallbladder does not produce bile. Gallbladder releases it. Gallbladder is the site for storage and concentration of the bile. Does that make sense to you? And we'll get back to this again. We're going to talk a lot about this. You with me so far? So gallbladder releases bile. Bile has two functions: neutralizes acidic pH, and it starts to solubilize, make solubilize or emulsify lipids, making lipids more accessible for digestion. Does that make sense? Because it takes time for the liver to pick up the processing the generation of the fat. Are you following? Like, if I would go and eat cheese, which is pretty fat, right? Fat. The initial solubilization of fat will be going on because of the bile release from gallbladder. And then my liver will pick it up. Are you with me here? Okay. Now, we still didn't get to CCK. What all you need to do is just to produce bile, and then how fat is going to be digested. Turns out that cholecystokinin also has effects on pancreas. And the effects of cholecystokinin is production of enzymes. So look what you have here. To kind of wrap it up, before we go on break. Look, team that gets an intestine has a low pH and high fat count. Low pH stimulates secretin, which stimulates pancreas to produce bicarbonate, and liver to produce bile. Fat stimulates CCK, which will release bile from gallbladder, and CCK stimulates pancreas to start producing digestive enzymes. Does that make sense? So bicarbonate plus digestive enzymes, we call it pancreatic juice. A good question. A good question. Pancreas and bile, are they primary or secondary digestive enzymes? Are they a part of alimentary canal? No, they aren't. So these two organs somehow have to empty their secretions into the intestine. Does that make sense? Something that you must know. So this structure here is called hepatopancreatic ampulla. This is the place where two ducts merge. One is a main pancreatic duct, which goes from, yes, pancreas, right? And another duct that goes in there is the common bile duct. Which is formed by the main hepatic duct. I omit the word bile. You can call it main hepatic bile duct. That's a bile duct, hepatic duct, which comes from, emerges from the liver, obviously, right? And cystic duct, which emerges from the gallbladder. Look what you've got. Liver produces bile. It gets collected. We'll talk about it. Gets collected, goes into the main hepatic duct. Does that make sense? And then gallbladder releases bile, which goes into the cystic duct. Both of these ducts merge into common bile duct, and common bile duct and pancreatic duct merge at the hepatopancreatic ampulla, and that stuff goes into the bilirubin. Does that make sense? Any questions? We good? Okay, we good. Let's take a 15-minute break. And we'll come back with that. So it's kind of an interesting opportunity for me and challenging at the same time, because the functions of small intestine, liver, and pancreas are very tightly connected into pancreas. Okay, So we've got a piece of a puzzle here. And I understand the irony of that statement. It's a puzzle by itself. But what I want to do now, I want to discuss sort of, what pancreas and liver do. And I'm going to start with the pancreas actually because it's easy, it's smaller, it's functional of sorts. And then move on to the liver because liver and the intestine anatomically and physiologically they're very, very tightly connected. Okay? So let's do pancreas first. I'm not going to touch on the anatomy, where it is located. Everything is there. Two things regarding pancreas, concept and kind of do a little bit of a promotional, cheesy promotional material. When I say watch the videos, watch the screencasts, I mean it. We have half of the time for our meeting. And after Thanksgiving, we go online. We're very limited. And I'm trying to cram as much stuff in this in-person experience as I can. This cannot be your course. This plus screencasts, plus review of this, plus quizzes, plus study guides, that's your course. It's crucial that you do. I do this shit, it's my 7th year. I know what I'm talking about. You see, I know that when I tell you do this, it's not because I enjoy giving you some extra work. You need to know this, and I give you all the tools. But so please watch stuff. Review, ask me questions. Totally fine. So 2 concepts regarding the pancreas that I want to read. First, how base is produced, how bicarbonate is produced. And I guess you won't be surprised to see that it's all the same story. We've got blood, right? And we've got CO2 from blood that is combined with water. That reaction produces carbonic acid. Carbonic acid dissociates into hydrogen ions and bicarbonate. This time hydrogen goes back in the blood, while bicarbonate is pumped into pancreatic ducts. And actually, this is the main way to produce acid or base in the human body. Does that make sense? Do you follow me? We will see it over and over again in cardiovascular and renal system and respiratory buffers, whatnot. Does that make sense? Second thing about the pancreas. If you will look at the slides, I'm not saying that you should do it right away, but here's a slide with the pancreas and all pancreatic enzymes. Okay? And what I want you to know for those pancreatic enzymes, their function. For instance, which of the following pancreatic enzymes breaks down carbohydrates? And I give you a list which will contain lipase, phospholipase, trypsin, and amylase. Carbohydrates, amylase. Make sense, right? Or the function of trypsin is to break down proteins and to activate other pancreatic enzymes. And this is the part that I want to specifically highlight. So it turns out that a huge chunk of pancreatic enzymes, when they come out of the pancreas, they are inactive. For instance, your pancreas produces a protein called trypsinogen. Okay? You see it in the list. So trypsinogen has to be activated. And what activates it? Enzyme called enterokinase. Enterokinase is a brush border enzyme. Brush border. It activates trypsinogen into trypsin. Does that make sense? Now, trypsin, what can it do? Trypsin can break down proteins, and it can take, say, chemotrypsinogen and activate it into chemotrypsin. Does that make sense? Trypsin will take pro-elastase and activate it into elastase. Trypsin will take pro-carboxypeptidase and activate it into carboxypeptidase. Does that make sense? Are we clear? This is not a hard concept. It's just something to remember. And I just want to focus here to emphasize. Yes, I'm going to ask about it. Okay? So no, for instance, I ask you, what activates chemotrypsinogen? What's going to be trypsin? What activates trypsinogen? Well, that's going to be enterokinase. And enterokinase is one of the crush proteins. Are we good? Are we clear? Not? Yes, go ahead. Oh, some of them are not have, they don't have to be activated. Does that make sense? So if I ask you like, does amylase require, well, not in that form, but basically, does amylase require activation? No, it's not, it's produced ready to go. Does that make sense? Some of them do require, some of them do not. We go to blood pancreas, move on to the liver. So with the liver, I want to focus on several concepts. First concept, again, I'm not talking anatomy. You'll do anatomy by yourself. One concept is, no, you good? Don't be afraid. The problem with masks is that I often cannot understand where the sound is coming from. Okay? So let's draw the liver and what it consists of. The liver, we're going to start with the elementary building block. The liver consists of lobules, and lobules are basically hexagonal structures. Okay? You will find in the text that there are plates of hepatocytes. Sure, I'm not drawing any frequent hepatocytes. Okay, good? What I want to highlight, in each corner of a lobule is located a portal triad. So you've got portal arteriole, portal veinule, and the bile duct. You with me so far? Bile duct. So this is called a portal triad. Now, look at the blood flow. So blood from, this is schematic. Don't take it as a like anatomically correct picture. Blood from portal arteriole and blood from the portal veinule. If I sometimes use vein and artery, same idea. They mix. Can you see them mixing? And they mix in the vessel that is called a sinusoid. I deliberately picked the color to show that it's a mixture of arteriolar blood and venular blood. We're good so far? So the direction of blood flow is towards the center, okay? And in the center, it gets into what's called a central vein. Does that make sense here? Good? So one more time, blood from both portal arteriole and both portal vein, get in the sinusoid, flows towards the central vein, and multiple central veins, they merge together, and collect the blood from the liver. Does that make sense? We'll get there. We'll get there. It's kind of a piece of the puzzle. Okay. So what is sinusoid? Sinusoid is very permeable vessel. So there's a lot of transport going on back and forth. Does that make sense? Meaning that, a lot of chemicals go in the blood, a lot of chemicals go from the blood into the liver. For instance, carbohydrates go in the liver, converted into glycogen, converted into triglycerides, fat in the liver being packaged into lipoproteins get in them. So it's a lot of transport back and forth. Good? Now, another vessel that goes through these, and there are multiple sinusoids, not just 6. There are like many sinusoids. Okay? That makes sense. Another vessel that goes in the opposite direction. It's not going from it's correct. It's not going from the central vein. It just goes from the liver. It's the bile duct. So your hepatocytes, liver cells, produce bile. Does that make sense? Good? They produce bile. Bile gets into the little bile duct at the corner of the lobule. All these bile ducts, they merge and merge and merge and merge. And eventually, all that bile drains into the main hepatic bile duct. Are we clear? We're good? There are a lot of macrophages in sinusoids because think of this. All that blood that gets into the liver, sinusoids are very permeable. There's some stuff in the blood. It's not supposed to be there, like macrophages. You good? Now I want to talk about a really important thing, a blood flow between the liver and the intestine. So you don't have to be very familiar with the circulatory system, okay? And it's going to be very schematic. Look at this. Let's draw some stuff here. That's going to be liver. Okay, that's liver, right? This is going to be heart. And this green one is going to be intestine. So I'm going to make certain statements, and you will tell me, please, let me know, like nod or blink or something. Give me some appreciation that, yeah, it makes sense. So heart pumps the blood to all the organs, right? Which means to the liver and to the intestine. Okay? Now, that blood is oxygenated. Blood that goes to the intestines gets deoxygenated. But what does this blood pick up in the intestine? Well, around. What does it pick up? What's the function of intestine? Nutrients, yes. So now we have deoxygenated, nutrient-rich blood leaving the intestines. The only problem is that nutrients that are picked up in the intestine, they have to be processed. And which organ processes the nutrients? Liver. So we need to get this blood to the liver. Does that make sense? So if we want to name them, I'm not going to ask you which blood vessels supply intestines. I'm going to put it on the picture. So we've got mesenteric arteries going to the intestines, right? And we have hepatic artery going to the liver. Are you following? And then we have hepatic portal vein going from intestine to the liver. The term portal vein, portal system, refers to the vein connecting to organs. We've already seen that. If you remember in the endocrine system, hypothalamus and anterior pituitary gland are connected by the portal system. Here, intestine and liver are connected by a portal system. We're clear. Look at these two, and look at these two. This portal arteriole is a tiny little branch of hepatic artery. Hepatic artery gets branched. This portal venule is a tiny little branch of hepatic portal venule. Does that make sense? The oxygen-rich blood from arteriole and nutrient-rich blood from the venule mixed together, go through sinusoids, end up in the central vein. Central veins start to merge like tiny little creeks into massive river. And the river that emerges out of the liver is hepatic, just hepatic vein. It's not portal anymore, just hepatic vein. Does that make sense? This hepatic vein enters vena cava, and vena cava, look, brings the blood to the heart. So heart now can distribute eventually pulmonary circuit. Yeah, we all know that. Yeah, but the point is, now you get nutrient-rich blood getting to the heart for the future distribution among the organs. Does that make sense? Are we clear? Okay. So we're gonna leave this at that here. And we're gonna talk, say a few words about the bile. So what are the bile components? The bile components are bile salts, lecithin, we'll get to this slide, mucin, bilirubin, bicarbonate. Now, look at this list. Let's talk about what the functions are. And we're going to go from the bottom. Bicarbonate neutralizes toxins, right? Remember that flow chart that we did with secretin and cholecystokinin? Remember? Okay. Now, bilirubin. Your red blood cells live for about 4 months. That's normal. And then they get destroyed. The problem is, heme component, one of the organic components, that iron in that organic compound, heme, it is toxic for kidneys. So it is metabolized to bilirubin. Unfortunately, bilirubin, well, it's not unfortunate, bilirubin cannot be excreted in the urine. Does that make sense? So bilirubin is excreted with feces. That's the function of liver, to excrete bilirubin. It is brown color. So that's what gives our feces brown color. Now, when does jaundice happen? When which organ is damaged? Liver. When there is a damage to the liver cannot efficiently excrete bilirubin. And instead of going into the feces and out of the body, it stays in your blood, attached to albumin, and it gives like your sclera slightly whitish color, your skin, not whitish, yellowish color, skin yellowish color. Does that make sense? That's failure to excrete bilirubin. Okay, mucin, sticky component. You need stuff to be sticky. Lecithin and bile salts. So what they do, and I'm going to make it very sort of schematic. Imagine you have some kind of a hydrochloric, that's oil, okay? How you make oil hydrophilic? Well, you need to solubilize it, emulsify it. That's your bile salts. These circles are hydrophilic heads. Does that make sense? And tails are hydrophobic. So you see hydrophobic tails easily interact with oil. Does that make sense? While hydrophilic heads make a perfect surface for, the watery environment in the intestine. Does that make sense? We're going to talk a little bit more about bile salts in a second, but kind of a good example. Next time you eat chocolate, check the ingredients. One of the ingredients will be lecithin. Don't worry, it's not coming from human bile. It's a plant lecithin. But just like bile salts, the lecithin is emulsifier. So when people make chocolate, good chocolate contains a lot of fat. That makes sense? A lot of fat. And in order for that fat to be evenly distributed throughout the chocolate bar, lecithin is essential. Does that make sense? Good? So we kind of, big things, excretion of bilirubin and emulsification of lipids. Okay, we're good? Remember I told you that we have to kind of go back. I don't have that picture. You should have it in the record. Remember I told you that secretin a little bit stimulates production of the bile, and cholecystokinin stimulates the release of bile from gallbladder, right? Now the question is, how the heck bile is being constantly produced at large levels? Like what stimulates bile more than secretin? And the paradoxical answer is bile itself. Let me explain. So bile goes into the intestine. Does that make sense? You can see. Bile. Right? Now, when nutrients are absorbed in the intestine, bile salts are absorbed in the intestine as well. And where do they go through these portal data? To the liver. In the liver, bile salts stimulate production of the bile. More bile goes in the intestine, where bile salts go into the blood, stimulate production of a bile in the liver. So that's a classic positive feedback loop, right? But then at some point, when nutrients are gone, digestion is gone, stimulation from secretin is gone, all this bile still produced. It's being produced a little bit. That makes sense? All this excess bile will get into which organ? Gallbladder. Okay? And in the gallbladder, the bile will be stored and concentrated. So next time when you eat something fatty, gallbladder releases the bile. It's good to go. The problem with concentration is that when you concentrate something, there's a risk for precipitate to be formed. Does that make sense? And that precipitate in the gallbladder is called gallstones. Gallstones are actually soft because the main component of gallstones is cholesterol. Bile salts are largely made of cholesterol. That makes sense. When gallstones are formed, if one of them obstructs the cystic duct, the drainage, the gallbladder starts to swell and becomes bigger and painful and inflamed. The person has to undergo cholecystectomy, removal of gallbladder, right? It's pretty fast. I know a guy who basically got sick on Friday, went in the surgery on Saturday, was back at work on Monday. It's fairly straightforward surgery. Can people eat fatty food if they don't have gallbladder? They can. Just be careful, because your bile is not going to be released right away. That makes sense. My favorite piece. Give me your hypothesis. Yes, or the largest gallstone ever removed from human body so that human was alive. Max. Give me max in pounds or ounce, whatever you think. What's the largest gallstone ever removed from? 2 pounds. You underestimate. Any other? None? You underestimate. 14 pounds. The largest gallstone ever removed from a woman in Britain was the size of a watermelon, weighed 14 pounds. Chile, right? I really have no idea. How can you not notice? That's my question. So now we figured that's basically all you like. Gallbladder is very straightforward. Stores and concentrates. That's enough. Okay. Now, few things about the liver. Let me think. Oh yeah, this thing. Look, follow me. So bile salts are picked up by the blood, go to the liver, stimulate bile production. Bile goes back in the intestine. Bile salts are picked up from the intestine, go into the liver, stimulate bile. That makes sense? That circle. This is called enterohepatic circulation. Okay? Now, what are the functions of the liver? I'm trying to think, concentrate. Okay. So functions of the liver, detoxification, we'll get back to this. Liver metabolizes toxins, okay? And processing of nutrients. So think of it this way. If when you eat carbs, the liver can store them in the form of glycogen. If glycogen storage is up, completely filled, the liver's going to store them as triglycerides, as fat. When you eat fat, it will just store fat. The liver will produce cholesterol and send it throughout the body for the synthesis of steroid hormones. Does that make sense? Liver will metabolize steroid hormones because they need to be broken down and then released with the body. That's really important excretory pathway for steroid hormones. That you produce the estrogen, I'm the only person who produces significant amounts of testosterone. Okay, you produce testosterone, just the ratio is different. So you produce estrogen, that estrogen has to be excreted at some point. It's liver, the body. That makes sense? You eat proteins. Well, amino acids eventually end up in the liver, and liver produces albumin, the key protein component of blood plasma in the blood. Liver produces clotting factors that are necessary for formation of blood clots and control of bleeding. That makes sense? To give an example, if you take a person and take both kidneys out, this person is going to live for at least a week, maybe 2. If you take the liver out, given that everything else is more or less intact, that's about 18 hours. Liver is crucial, super important organ. By the way, second largest. Okay? So far, does that make sense? Now, I want to go back and kind of give you some clinical examples for detoxification. What toxin is most commonly associated with liver dysfunction? Alcohol. So, consumption of alcohol, abuse of alcohol, forces liver to, detoxify, which leads to actually death of liver cells and inflammation in the liver. That makes sense? Inflammation usually results in the formation of a scar tissue. And, inflammation results in the healing. Healing is a scar tissue. The problem that scar tissue in the liver is a connective tissue. That connective tissue doesn't work. It's not hepatocytes, right? So liver becomes less and less efficient of sorts. It does not perform its function well. So what are the consequences? What can you see in a person who abuses alcohol, like seriously abuses alcohol? One of the consequences is problems with albumin synthesis, which leads to and we'll get back to this when we talk about circulatory system, leads to edemas, peripheral edema, like swelling in the legs and arms. Bloating, you're not going to notice it you're not going to notice it that much. So. But the funny is that's a true story. I'm sorry, that's a true story. I had a student, one of my first years here, and we were talking about this process, and I told him that look, the liver's damaged. It cannot properly excrete joy hormones. And in males, it results in a very interesting thing. Testosterone is in liver, it's converted to estrogen. And this estrogen is supposed to be excreted, but it's not. So estrogen levels in people with a severe liver damage, with cirrhosis, start to rise. And what happens to a man whose estrogen levels go up? This man starts to develop secondary sex characteristics of a woman, namely gynecomastia. And a student, it was this room before the renovation, she was sitting right there, okay, like right next to Casey, and she said, "Now I understand why those alcoholics grow tits." That's actually what happened. That's pretty advanced. She was working with folks who were like in rehab for really bad alcohol. That makes sense? Another interesting feature that you may notice when kind of liver gives up, these things, bile salts and lecithin, are essential for fat processing in the intestine, right? But if you have gives, bile, then this fat is not being properly digested, not being properly absorbed. People develop what's called steatohepatitis, a fatty stew, which will then float because lipids are so light. It's a pretty characteristic thing, actually. If even one time heavy drinking may lead to steatohepatitis, because liver, especially if you like drink a lot of alcohol and eat fatty food, your liver says, "Screw that, I'm giving up." Okay, and next day you go to the restroom and you're going to see that feces are going to float. They're going to smell horribly. That's one of the features of steatohepatitis. And they're going to be grayish because bilirubin is not properly excreted. Does that make sense? So color that. Good so far? Somebody asked me, yes, liver can repair. Yes, it's true. So basically, if someone had a drinking problem and there's some cirrhosis, but then quit drinking, eventually will start getting functional. Any questions? Okay. We are doing absolutely marvelous in terms of time. Okay. While I'm cleaning it up, I really kind of a bit nervous about it. The brush border enzymes and pancreatic enzymes. Did I make myself clear what I wanted? Function for each enzyme, and specifically for pancreatic, that story with activation. Like trypsinogen is activated by enterokinase into trypsin. Chymotrypsinogen is activated by trypsin into chymotrypsin. Pro-elastase is activated by trypsin into elastase, and so on and so forth. Yes, that I ask you to know. Good, clear? So brush border enzymes do not require any activation, period. But there is one brush border enzyme called enterokinase, which activates trypsinogen into trypsin. And then trypsin activates a bunch of other enzymes. Well, just that. And what they do. It's not going to be, I'm not going to throw any curveballs at you. But let's say if I ask you which of the following enzymes participates in the digestion of protein, then don't pick amylase or lipase or phospholipase or nuclease. Does that make sense? Yeah, that's it. And the reason why I ask you so much frequent quizzes, because you get examples of the question that you're going to see. Does that make sense? Okay. So let's talk about absorption of nutrients. We're not talking about water and ions yet. We're going to talk about nutrients. And we're going to start with the absorption of carbohydrates. Okay? So we're going to throw some terms here. I'm going to actually draw two cells. That's two. So that's the lumen of intestine. Okay? This one here is blood. Right? You following me so far? Nothing too complicated. Okay? So we're going to start with a very simple concept of what happens to sodium. We're going to, and remember, this is an apical side of the cell. Okay? That's the epithelium, columnar epithelium. So the side that faces lumen is apical side. The side that faces blood is the basal side. Okay? Good so far? Let's talk. So, what's going on at the basal side? The basal side you have, and they have a pump, sodium potassium pump. That pumps sodium out of the cell into the blood. Does that make sense? Some of that stuff is obviously a little bit of oversimplification. Obviously, it's not pumping directly into the blood, but for our intents and purposes, we can think of it being pumped into the blood. Are we clear? Goes in the blood. Since sodium is being pumped out of the cell, what would be the concentration of sodium inside of the cell? Low or high? Huh? Low, yes. Not just low. It's going to be much lower than the concentration of sodium in the lumen. Does that make sense? So concentration of sodium in the lumen of intestine will be higher than in the cell. Good? So sodium will be able to diffuse into the cell. Does that make sense? Here's the question that I have. So, what's going to happen to that sodium that goes into the cell? What's going to happen? That's simple. Yeah, it'll be pumped into the blood all the time. Does that make sense? So essentially, the function of that pump is to maintain low concentration of sodium inside of the cell so that sodium can diffuse from the lumen of intestine into the cell. Am I clear? Here's the deal. Now you need to somehow get, say, glucose being absorbed. Now the concentration of carbohydrates inside of the cell is higher than outside. Does that make sense? So can they diffuse if the concentration in the lumen is low and the concentration in the cell is high? Can they diffuse from the lumen? From the lumen? No, they cannot diffuse against the gradient. Does that make sense? They have to be pumped. Here's how pumping works. So you've got sodium that diffuses from the lumen into the cell. Does that make sense? That diffusion provides energy for active transport of, say, glucose to go against its concentration gradient and get into the cell. Does that make sense to you? Clear? So what we have here, I'm going to reiterate it one more time. Sodium diffuses into the cell. Why? Because concentration of sodium in the cell is low. Why? Because there is a pump. Got it? So sodium, because there is a pump on basal side, sodium can diffuse through the apical side. The kinetic energy of that diffusion then is used to pump glucose, to pump glucose from the lumen into the cell. Does that make sense? Now, I told you that the concentration of glucose in the cell is pretty high. So now glucose can diffuse through the basal side. So sodium is being pumped on the basal side, but diffuses on the apical side, while the glucose is pumped on the apical side and diffuses on the basal side. And what is the driving force? Sodium potassium pump, right? So look at the steps. Sodium potassium pump keeps intracellular sodium low. That enables sodium to diffuse. Sodium diffusion through the apical side enables active transport of glucose through the apical side. Then glucose can simply use facilitated diffusion in the basis. Am I clear? That makes sense? You know what's cool? For amino acids, just replace glucose with amino acids. Exactly the same way. I'm not going to draw it because it makes no, like, everything is the same except for the word glucose here and there. Got it? Okay. By the way, this molecule here that uses the diffusion of sodium to pump glucose, it's called synthol. Okay? Good. Okay. Now let's talk about fats. We have enough time for it. What's the difference? So you start with a big chunk of fat. But again, when I say a big chunk of fat, don't perceive it as like, you eat a pork chop and you have like this fist-sized, ball of lard going through your digestive system. When I say chunk, it's a droplet, okay? That makes sense? It's a droplet, maybe a few millimeters in diameter, maybe less than that. So before we move any further, I want to ask you, that's a simple question, but not a trivial question. So this is a globule of fat, okay? Now what I do, I break this globule down into 5 smaller ones. Which of these formations, this or this, will have higher surface area? So what's going to have bigger surface area? One large sphere or 5 small spheres? Huh? Yes, 5 small ones, right? And digestion of fat will inevitably happen. Like all the enzymes will be working on the surface. Does that make sense? So if we want to digest things most efficiently, we want to break them in pieces as much as we can. Smaller and smaller droplets. Does that make sense? This is called emulsification. This is what I was talking about when I talked about bile salts. Remember I gave an example, if you try to mix oil and water, not going to work, right? But if you add a bit of a soap, and that's actually, you can do it like an experiment at home. If you have a greasy skillet, pour some water in it, and you will see this kind of huge fat blobs on the surface. You know what I'm talking about? And then take the dish soap and add a couple of drops. And they disappear. You still have a lot of droplets, but they're very, very small. And they have very uniform size. And right there. So what essentially happens with a fat is that it, together with the bile salts, forms mycetes. That makes sense? This is called a mycete. Okay, we're good? So now, what exactly is going on inside of the mycete? If you think, like, okay, we solubilized fat. It's now in the form of a very, very fine emulsion, very, very fine droplets. Don't take it as a, like, it's a fat inside, and now it somehow, in some magical way, it's going to get digested. No, mycete packages not only fat, but also, of course, enzymes that break it down. Does that make sense? And those enzymes, lipases, what they're going to do, and we're going to focus on specifically triglycerides, we're going to break down triglycerides into monoglycerides and fatty acids. Now, let me illustrate it for you. I think the chemistry here is really important. This, look at this. This is glycerol. Now, I'm going to limit my writing. I'm going to change some things. Okay? I'm going to draw a big ass bond right here. Purple is glycerol, whatever, violet, okay? This color, whatever it is, that's probably purple, right? That's fatty acids. Does that make sense? This whole molecule is called 3,3 glycerol. Am I clear? Does that make sense? So what lipase does inside of that mycete? It forms two fatty acids, 1 and 2, it's hydrolysis of fat, and monoglycerol. Does that make sense? So we've got two fatty acids, monoglycerol. Are we good? So we can put it in the mycete right here. It's going to be really small. Monoglyceride and fatty acids. Okay? This mycete is then gets absorbed into the columnar. Okay? And inside of that, and the reason for triglyceride to be broken down into a monoglyceride and two fatty acids is to make it a little bit more hydrophilic. It's easier to get it into the cell this way. Does that make sense? So once monoglycerides and fatty acids are in the cell, they recombine, forming 3 glycerides. So what essentially happens, look at this. So what happens in the cell is this bond part is stored back. Think of it this way. You need to move in a pretty big pouch. Like, a section. You're not going to carry a sectional into your house, right? You're going to put it apart just a little bit. Not completely, not to the very little bitty detail. But you're going to put it apart and then move it into the house and put it back together. Does that make sense? Think of it the same way. We cannot move in the whole triglyceride molecule. We need to put it apart, squeeze it into the cell, put it back together inside of the cell, back into triglyceride. We good so far? What happens to triglyceride then? Turns out, well, this is fat, and our blood is water, right? Plasma is water. Can we mix fat with water? Successfully, not really. So what we're going to do instead, we're going to use triglycerides with some proteins. We'll beta globins. And protein and triglyceride together, they form, this is called chylomicron. Basically, a large assembly of proteins and fats. Does that make sense? And these proteins and fats, they go into the lymph. Am I clear? This green vessel, it's kind of, this green vessel right here, is called black tube. It's a lymphatic vessel that absorbs fat. Does that make sense? So the fat is carried from your intestine, not by blood, but by lymph. Eventually, though, that lymph ends up in the blood. And then all these chylomicrons get to the liver, where they are being processed. Fat is either stored or being repackaged, used for cholesterol synthesis, used for synthesis of lipoproteins, and sent to other tissues. Does that make sense? So I think I have an image in the notes of plasma with different concentrations of chylomicrons, like 4 tubes, and they are differently, they have different turbidity. Basically, put something very, very, very high, and then take a blood sample afterwards. You're going to see this chylomicrons. I know that it can mess. There's an old test. I don't know if you've been with it. Fairly straightforward blood test for syphilis, called Wassermann reaction. And the point is that you take the blood draw, then you have the agent. I don't know which one. You have the agent you test blood. And one of the things that people are told not to do before they do blood Wassermann reaction, not to do it either. Because it will claudicate plasma and will produce the reaction. And I know that the story of a nursing student, they were kind of, well, not nursing, med tech, back in Russia. She was practicing Wassermann test, completely forgot, ate some fatty stuff in the morning, went to class, took a blood draw, ran the reaction, it's positive. She was terrified. She thought that she had syphilis and then realized that it wasn't positive, which is false positive. Okay. So, kind of, one more time going over this. So for carbohydrates and amino acids, monosaccharides and amino acids, it's sodium pump on the basal side that maintains low sodium concentration in the cell, which allows for the for transport, diffusion of sodium and diffusion through the absorption of the through the importer on the apical side, and then glucose or amino acid will diffuse, use facilitate diffusion. For fats, solubilization first. Okay. Inside of the mycelium, the glycerides are broken down into monoglycerides and fatty acids. Go into the cell. Okay. Reform triglycerides. Triglycerides are packaged with the proteins to form chylomicrons. Chylomicrons enter the lymph, and then eventually from the lymph enter the blood and the liver. Question. Does that make sense? Question. Good? Okay. Marvelous. The exam's going to be 2 weeks from now. We're going to finish the